Welcome, everybody. My name is Slava. I work for Google. And today I'm going to talk about watermarks, which is how we measure time and progress in streaming systems, such as Apache Beam, Google Cloud Dataflow, and beyond. So first of all, by show of hands, how many of you use Apache Beam or have heard of Apache Beam or Google Cloud Dataflow? So most of you have at least heard of it. Yeah, very cool. So for those of you that aren't too familiar with it yet, Apache Beam is a collection of SDKs for building parallelized data processing pipelines for both batch and streaming. And Google Cloud Dataflow is a Google managed service for executing such pipelines on top of Google Cloud infrastructure. So first I want to start by giving you an example of what such a pipeline might be like. And the example I want to give is the example of Twitter hashtag auto-suggestions. So let's say you start typing in a hashtag prefix such as AR, and the auto-suggestions that will pop up will be something like Argentina or arugula rocks or Argyle socks. And we want to answer the question of how do we build such an auto-suggest engine, right? How do we create a mapping, essentially, from prefixes to relevant suggestions? So it would look something like this. We're going to start out with some data. Let's say it's the set of tweets for the last day. And we're going to want to go to a set of predictions, which is a map of prefix to a list of relevant suggestions. So we're going to read in some tweets. It's going to look something like this. It's going to say, hashtag Argentina scores, or watching hashtag Armenia versus hashtag Argentina, and so on. And what we're going to want to write out are a mapping of these sets of suggestions, what prefix maps to what relevant completions. So for our example, the next thing we're going to do is we're going to extract the tags. Here I'm describing just the transformations that we're going to have to do on our data to go from the source data that we have to the result that we want. We're going to extract the tags because in our example, we only care about the popularity of each tag, let's say. And the tags are going to be in Argentina, Armenia, and so on. We're going to count them up. We're going to want to count them up because, like I said in our example, what we want is the popularity of each tag to influence its rank in the suggestion. Once we've counted up the tags, what we really want is we want to know the prefixes that are generated by each tag. So we're going to expand each tag to the set of prefixes that it generates. So Argentina is going to expand to A, AR, ARG, and so on. Armenia is going to expand to A, AR, ARM, and so on. And finally, once we have that, we can just take the top 3, let's say, tags for each prefix. And that gives us exactly the results that we want. So what have we done here? We've described just a set of logical transformations that we've had to perform on our data to get from the source that we have to the result that we want. How would this look like in code if we were using Apache Beam? Well, it would look something like this. For each line of transformation that we described previously, there's a line of code here. And I want to call your attention specifically to the lines that say read, count, top, and write, because these are built-in SDK primitives that you as the user had to do no additional work to make use of. Conversely, there is extract tags and expand prefixes, which are functions that you wrote as the user and then passed into these parallel do, par do invocations that make sure they run in parallel over your data. And just to show you there's no magic going on here, if we look inside this expand prefixes function, it's very straightforward. All it does is it loops over our input element and expands it to its possible prefixes. So OK, so we have this little pipeline. What can we do with this? This is a batch pipeline that we wrote because it reads from a batch source, text.io. And now we can run this pipeline. We can run it on top of the Google Cloud Dataflow framework. We can run it on top of other runners, such as Spark or Flink. We can run it locally on our machine using the direct runner. So there's a host of possibilities of where you can run this. For our example here, what we're really interested in is we're interested in the streaming case. How do we turn this batch pipeline into a streaming one? So to do this, let's make our example a little bit more interesting, first of all. Let's say that instead of reading from a batch source, we're reading from some stream. And what's going on is there's a football match going on between Armenia and Argentina. And as time goes on, let's say before the football match begins, the most relevant suggestion for the prefix AR is Argyle. As the game begins and Argentina scores a goal, the most relevant suggestion, the most popular thing that people are tweeting is Argentina goal. And that's what we should be returning as part of our auto-suggest. As the game draws to a close and Armenia wins the game, the most relevant thing that we should be returning at that point is Armenia rocks, because that's the most frequent thing that people are tweeting. So how do we take the batch pipeline that we wrote just a minute ago and turn it into a streaming pipeline that gives us this desired result? Well, first of all, we're going to have to change our sources, right? Instead of reading from a batch source like a text file, we're going to want to read from some streaming source. In this case, I used PubSub, which is a Google Publish Subscribe system, which we'll talk a little bit more about later. So OK, we're reading from PubSub. What else are we going to want to do? Well, we said that we want the results based on the most recent window of data, so maybe the most recent 60 minutes. So we're going to take our input, and we're going to window it into a sliding window of 60 minutes. And that's going to give us our desired result. It's going to give us data from the last 60 minutes of time. So we're done, right? Great. We have our desired result. We're happy. And if all you want to do is write a pipeline, maybe you are done. Maybe this is the end. But for the purposes of our talk, we really want to understand what it means to window data into the last 60 minutes worth of time. Because that's a very non-trivial operation, right? If you're operating on large distributed streams at massive internet scale, windowing data into 60 minutes of event time is very non-trivial. So, how are you going to do this, right? There's some obvious suggestions you might try. You might say, OK, every time the clock passes an hour mark, you're going to trigger some aggregation. Well, that doesn't really work, right? That doesn't really work because, first of all, if some source gets delayed, you might miss out on some of the data. Conversely, if that source was delayed and now is catching back up, you might get more than an hour's worth of data in the window. You might not get the right hour's worth of data in your hour window. So really, there's probably no good correlation between the hour of data or the time of data you're getting and the hour of window if you use just the wall clock time. So you need something better. And really, the question that we want to ask is more fundamental, which is, how do we even know if the pipeline is keeping up, right? If we can answer the question that the pipeline is keeping up, then we can answer the question of when should we trigger our aggregation. Streaming is different than batch for this, right? With a batch pipeline, you can say, I've processed 37% of our input, so we're 37% done, so great. With streaming, we can't do that. We never know when we're done, so we need to look at something else again. A natural inclination might be to look at rate. Rate gets you some of the way there. Rate tells you that you're maybe doing well, but it doesn't tell you if a particular record is stuck and not making progress through your system. If one record is stuck and not making progress through your system, that may fundamentally change your result. So you really need to know about every record. So we need a different definition. To get at this definition, I want to look at a streaming process, any pipeline that's processing streaming data, as a black box for a second. We have input going in on one end, so we're receiving messages. We're doing some sort of processing in this black box. Doesn't matter what the processing is. And we're writing some sort of output on the other side. We can consider the messages that are coming in as being tagged with an event time. This is an anchor in time that corresponds to the actual time of occurrence of the event. So if we're processing a Twitter feed, then the time that the tweet was written or published may be the event time. If we're processing some mobile event, like a user clicks on something in an app, then the time the user actually made the click would be such an event time. And it's reasonable to suppose that almost any form of data that we're processing in a streaming pipeline is going to have such a logical event time associated with it. In the context of a streaming process or a streaming pipeline, we can then look at the distribution of the event times that are coming in. And we can consider all of the event times that have been received by this box and are still in flight, but have not yet been completed. That sort of forms the red part of the graph there. As the events are being completed, they're being added to this blue part of the graph. And as time goes on, this graph sort of moves to the right, and this red sliver sort of keeps moving to the right, and parts of the red are becoming blue. So I want to call your attention to 2 points in this graph. One is the point far on the right, which is now, it's real time. And then there is the furthest left red point on this graph, which is the oldest unprocessed data. And that's the intuition that we use to form our notion of progress. We define a watermark or a low watermark of a streaming step or a streaming process or a streaming pipeline to be the timestamp of the oldest unprocessed data, or the oldest work that hasn't yet been completed by this step. So we've given you this definition. I want to now argue that it's a useful one. I argue that it buys us two key things. It buys us visibility and it buys us actionability. By visibility, I mean that if the pipeline is not keeping up, the watermark cannot advance, and we'll know about this. And the delay between real time and the watermark tells us the delay and the latency of our streaming process. The other thing it buys us is actionability. If we can define the watermark to be monotonic, and if we can somehow get rid of late data, which we'll talk about in a minute, we can say that when the watermark passes a certain time t, we can correctly emit all aggregations as of time t. So if the watermark is 1 o'clock, we can emit the hour from 12 to 12:59, because we know that we're not going to be getting any more data for that window. And a lot of the data flow windowing primitives are built on top of this concept. OK, so we've defined the watermark, but now let's sort of look inside our black box. If our black box was a streaming process or a streaming pipeline, then within it, it's actually a pipeline, right? There's components there. So you might have some pipeline that has a fan out and multiple stages processing that fan out and then fans back in. So in fact, we define watermarks at the boundaries of these steps. So for each streaming step, we can define an input watermark and an output watermark. And we define each in terms of the other. The output watermark is the minimum of what we're currently processing in the step, and the input watermark to that step. And the input watermark is the minimum of everything upstream of that step. So what would that look like? We define the input watermark at the input to a step, the output watermark at the output of the step to take into account what's being processed at the step. So the output watermark will always be lower than the input watermark. And we can formalize the definition a little bit here. And in a graph, that will mean that the input to stage 3 is the minimum of the outputs of stages 2A and 2B. The outputs of stages 2A and 2B will be the minimum of what's being processed in stages 2A and 2B and their inputs. The inputs to stage 2A and 2B will be the output of stage 1 and what's being processed in stage 1, which is the minimum of the input to stage 1, which leads us to the critical question. What is the input to stage 1? So we'll talk about that in just a second, but first I want to say that if we can make this definition, then we can track data perfectly throughout the system, right? We've pushed the problem of defining completeness onto the source, and we've tracked data perfectly through the rest of the system. So if our source can give us complete information about the timestamps of the data, then the rest of the system will also be perfect. And we can make aggregations anywhere in this pipeline that are perfect. If the source is imperfect, then the rest of the pipeline will also be imperfect. But the rest of the pipeline will not create additional late data. So let's get back to this question of how do we define the watermark at the source? Well, watermarks at sources are highly specific, right? We need to know something about the source. And we cannot always predict the future. There are some cases where we know a lot about the source and we can give a very good watermark. There are some cases we know very little about the source and we can't give as good a watermark. The reality is that late data will always happen because we cannot predict the future. And we label such messages as late data that come in behind the watermark. We do our best to minimize them, and then we provide very specific semantics in data flow in order, and in Apache Beam to process them. And for more details on that, see Ken's talk right after mine here. He'll get into a lot of the nitty-gritty on this. So I think it will be good to step through an example to sort of understand how watermarks work in a real pipeline. For our example, we're going to assume a couple of things. We're going to assume that there's no late data, first of all, and we'll talk about how to relax that assumption a little bit later. And we're going to try and model the beginning of our example pipeline from before, our pipeline with tweets. So in this picture, we have a pipeline. It's reading from PubSub. It's reading into a stage, which is then shuffling it into a second stage, which is windowing that data into 1 hour aggregates. So that second stage will buffer up the data and emit aggregates on our boundaries when it's time to do so. And we also have a component in this picture that we call the watermark aggregator, which is kind of like a scoreboard. It keeps track of all of the watermark values for the rest of the pipeline. We initialize the system with 2 special values. We call them unknown and empty. Unknown means we don't know anything about the watermark, so we can't advance it past negative infinity. Empty means we know that there is nothing being done here, so this value should not delay the watermark, which we set to positive infinity. And of course, we initialize the system to unknown. We don't know anything about PubSub yet. This propagates all the way down the pipeline, so all the input and output watermarks are also unknown. We notice, though, that the in-process watermarks of stage 1 and 2 are empty because the stages are quiescent. Nothing is being processed. First thing that happens is we get some notion from PubSub that we're not going to see any messages older than 1 o'clock. Once we get that, we can propagate that down the pipeline to the input of stage 1, to all the shards of stage 1, to the outputs of stage 1, all the way through the pipeline to stage 2. Well, that happened. All right, there we go. So from here, the next thing that might happen is we might get a message. That message will have some timestamp that should be ahead of 1 o'clock, right? Because PubSub gave us a promise. PubSub gave us a promise that we're not going to see anything older than 1 o'clock. So that message might have some timestamp at 1:01. That message will get shuffled to stage 2, and will get buffered inside stage 2, which will then delay the in-process watermark of stage 2. This will continue. The PubSub watermark may now advance. More messages may arrive. And eventually, the PubSub watermark will advance, let's say, to all the way up to 159. And these messages will be all buffered in stage 2. Eventually, the PubSub watermark will advance to 2 o'clock. This will propagate all the way down to stage 2, at which point we will be able to emit the aggregate from stage 2 that has our hours worth of window between 1 and 2 o'clock. This is, of course, all without late data in the picture. So what are the takeaways from this example? One is that any delay in an upstream stage will delay a downstream stage, and this is by design. This will ensure that no aggregation can occur downstream unless we have all the messages upstream that we need, unless we finish processing all the messages upstream that we need. This works well, as I said, if we have good watermarks at the source. So what about late data? Well, one thing that we make sure of is that we make sure that the watermark is monotonic. We could handle late data in multiple ways, right? We could say, let's not make the watermark monotonic. Let's allow it to move backwards. If we did that, then aggregations would be allowed to fire multiple times, and then we wouldn't be able to have side-effecting aggregations, not very easily anyway. So instead, we allow the watermark to only be monotonic, and we provide special semantics using triggers to handle late data, as well as trying to minimize the amount of late data that we see. So let's talk about how we provide watermarks at the sources. We've said, we try and do a good job of making sure we don't have late data. So let's talk about how we would try and do this for a couple of different representative sources. I'm going to look at two examples. One is an easier case where we're reading data from log files, where we know most things about those log files, and a harder case where we're reading from an opaque source, such as PubSub. So for log files, let's say you have a bunch of log files. Data is laid out in mostly event time order in these log files. You're reading them possibly from a distributed set of processes. But for the most part, the picture is easy, right? You try and keep up in each of the log files, and low watermark really becomes the measure of the low watermark on each of these files. Of course, in reality, things get a little bit more complicated. Servers might fall off the network, and we'll lose track of them. Then they'll come back, and they'll have late data. Files may be growing as we're reading them. Files may have events out of order. So the reality does get a little more complicated, but at least conceptually, the picture is easy. A more complex example is PubSub, right? PubSub is a publish-subscribe framework that allows a set of distributed senders to send data to a set of distributed receivers. There's no synchronization between senders and receivers. There's no ordering guarantees. So data really can come in and out of the system in any order, and we don't know anything about the data that's buffered inside PubSub. PubSub doesn't keep track of event times, any application level metadata for that matter. So PubSub can't tell us what the oldest message from our perspective is within their buffer. So how do we build a watermark for such a source using only information that's available as a client of PubSub without sort of inspecting the internal state? Well, one way to do this is to look at something PubSub does give us, which is the oldest unacknowledged message. PubSub works by delivering messages. We pull those messages off of PubSub. When we're done processing them, we acknowledge them, and they're removed from the PubSub backlog. Until we've removed such a message, it delays the timestamp of the unacknowledged message in PubSub. That timestamp comes from the time that the message was published to PubSub. At the point you've sent a message to PubSub, it gets timestamped, and that timestamp is now stored. The oldest such timestamp is available as a measure of backlog in PubSub. This timestamp is not the same as the watermark. It's not the same as our event time. For example, if you're reading from a historical source, that timestamp will have nothing to do with the timestamp of the actual message that's being ingested by PubSub. So how do we use this timestamp in order to establish a watermark? Well, imagine you have a stream that you're consuming from PubSub. Messages on this stream have two timestamps. They have the publish time and an event time that PubSub doesn't know about. And I've labeled messages in black and red here for ones that have been processed and completed, and ones that are not yet acknowledged. They may have not been received yet. They may have been received but not processed and acknowledged. So we don't really know where those messages are. What we do know is that there is a boundary, an oldest unacknowledged boundary here, behind which all messages are processed. We cannot look at just the set of messages we have received ahead of that boundary in order to determine the watermark, because we don't know which messages we're missing. However, we can set up a second metadata-only subscription that does not do any message processing, but only looks at the metadata. Because it only looks at the metadata and does not do any heavy lifting, it can always keep up with the stream. Once we've done this, we can use it to inspect the backlog between the oldest unacknowledged on our original subscription and real time, and use those values to inspect the event times that we care about to establish a watermark. So what is the takeaway here? The takeaway here is that watermarks allow us to reduce the complexity of tracking progress and completeness in a streaming pipeline to the progress and completeness of a source. If we can model a source well, then the rest of the watermarks in the pipeline will also work well. And in practice, there is no one-size-fits-all solution for sources. You have to know something specific about each source in order to model its watermarks. I've shown you a case for log files. I've shown you a case for PubSub. And there are other cases that wind up working extremely well for other sources. Never perfectly, but extremely well. And extremely well is often good enough as long as you can provide good late data semantics. One more thing I want to talk about. Let's see how I'm doing on time here. One more thing that I want to talk about is system watermarks. We've talked a lot about watermarks, and they've been implicitly data watermarks. These are watermarks defined on top of the data timestamps of the events. But we can also look at watermarks based on the system events that are used to process this data. So every time that we send an RPC to shuffle messages between stages, that's a system event. And we consider it running until it completes. Every time we trigger an aggregation, that's a system event. We consider it running until that aggregation completes and is persisted back to persistent store. By creating watermarks off of system events, we're able to distinguish data delay from system delay, which is critical. Let me show you why. Imagine we have this graph here. We know that our data is falling behind. We know that as time moves to the right, the watermark is falling behind. But can we tell what's going on? Well, there are actually several cases possible. One case is that our system watermark is falling behind. This really corresponds to the fact that we had some data that was in flight, and as time progressed, that data is still in flight because some system event did not complete. Maybe we sent an RPC to shuffle data from one stage to the other, and that RPC is not completing. This is different from the case when our data delay is going up, but our system delay is not. In this case, we know that the system is performing perfectly, but our data delay is going up. Why is that possible? Well, maybe we have a windowing aggregation. Our data is sitting there delaying the watermark while we're waiting for the window boundary to pass and for our window to fire. So this is an important distinction from a visibility standpoint that lets us distinguish between a delay in the system that's preventing processing from happening versus a delay in the data that's legitimately part of your computation. Another use of system watermarks is a system we call exactly once. Dataflow and Apache Beam support exactly once, which is at least once processing and at most once processing. For at least once processing, we need to make sure that we retry. That's pretty self-explanatory. But for at most once processing, things get a little more complicated. We need to do some deduping. And in order to do deduping, we need to store a lot of state. State is expensive, so we do a bunch of different optimizations. One optimization we do is we use Bloom filters, a set of Bloom filters, to reduce the number of reads that we have to do and reduce the amount of in-memory store that we have to use for our deduplication. Another thing we want to do is we want to garbage collect the exactly once data from persistent store as quickly as it is correct to do so. System watermarks allow us to do this even in the presence of late data. You couldn't use a data watermark because then all late data would show up as duplicates, or possibly show up as duplicates. So, hopefully, what we've taken away from this talk is that watermarks are a good way of defining progress and completeness semantics on a streaming pipeline, and that we can build rich windowing semantics on top of watermarks that you'll learn more about from Ken. And most importantly, that watermarks are only really as good as the source. If we can model the completeness of a source well, then we can model watermarks well throughout the rest of the pipeline. And that there's also a distinction between, that we can draw between system and data watermarks that allow us to distinguish between system and data delay. Thank you.
So are there any questions for Slava? Lots of time.
Go ahead.
When data is late, are there ways to detect if data is incomplete and somehow handle that as
Can you say more about what you mean by incomplete? Oh, I see. You mean that we don't have the full...
timestamp, but it doesn't contain all the data that we need.
Right. So the question was, if data is going to be late, can we somehow predict it in some cases? Is that the same way of saying your question?
Is there some way of checking the completeness of the data, not just the lateness, and using that to set your early watermark?
Yes. So the question is there some way of checking the completeness of the data, not just the lateness, to basically delay the watermark until we have that data? That, again, boils down to the question of the source. In some cases, yes. If we're reading from log files, for example, we might know that we expect a log file, and that log file is absent. Or we might know that we expect like a shard to be there, and that shard is absent. So again, it boils down to what we know about the source. If the source is something like pub/sub, then no, we can't, because we don't know if a random client is suddenly going to inject one message. And this may be a client we've never heard from before, we've never seen them before, and it's just going to inject one late message and then go away forever, right? So there are cases where you can, and there are cases where you can't, and it always depends on the source. Does that answer your question?
But there's some mechanism for setting the watermarks within the system so that you can use those business rules to decide.
At the source. So in Dataflow, we currently do not have a way to do this programmatically. In Millwheel, which was the progenitor for the Dataflow streaming execution engine, there is a way to do this by giving users an ability to model the source logic, essentially to delay the watermark if you know something more about it. Our goal with Dataflow is to provide as good tools as possible for each kind of source, right? If you're writing your own source, you have a custom source, and there is a way to do this, right? If you have a custom source, you can set the watermark based on what you know about that source. If you're using an off-the-shelf source, you wind up using the source watermark implementation that the streaming engine writes. So for Dataflow, that's something that we write. Does that answer your question? Okay. You mean, so you're injecting data from like an off-the-shelf source such as pub/sub, but you know something more about it? Yeah. Right. Currently, not directly, although you may be able to do something by creating an additional custom source that does it, but still inject the data through, a pub/sub channel, right? Right, something like that. So that's not the best tool, but I think you could do something like that to model your specific semantics. Yep, go ahead.
So I have a question about the watermark aggregator.
Uh-huh.
Maybe it's just how it was presented in the slides. It seems that there would be some sort of capturing metadata for one record that's going through the stream for every process step.
Right.
How is that metadata stored? Because it seems like you get it would explode.
Sure. So that's I didn't dive into that too much. The question was about the watermark aggregator and basically how do we implement tracking all of these message timestamps without exploding our state. The way that we do it is we actually store histograms in all of the shards of our processing. So as data is flowing through our processing stages, we store histograms about the timestamps that exist in each of the buffers. We send minimized representations of those histograms to the watermark aggregator, which then itself minimizes them and forwards the minimized value onto the next stage to use as part of the minimum for its set of histograms. So we minimize at every step, and we only store histograms of the event times to reduce the amount of state that we store. Yep.
Are you aware of terminology around probabilistically determining the likelihood of late events? I mean, I realize it all matters depending on the story. Is there a formal literature on that?
I don't know of formal literature, although that's a really good question. One thing I can say is that internally we've done something with probabilistic watermarks, essentially, by modeling the distribution, by taking the watermark on the distribution of event times rather than taking just the minimum. By doing this, you increase the amount of late data that you have, but you also allow a smoother and more quickly advancing watermark. And you can in many cases, bound the error by saying, well, given this distribution, I will have less than 1% late data, and our watermark moves at 99%.
You're basically watching the watermarks themselves with the probability on top of that. What's normal, if you will.
Correct. It doesn't, it's not a formal way of doing it because you're not guaranteed any distribution by any source, but it's sort of, I think, in the spirit of what you're saying. And it's a really good question about literature. If you find some, forward it to me. Other questions? Yes?
You went to the test on how to the watermarks and you didn't get how you with the two you get the watermarks.
Sorry, can you say which slide was the in PubSub? Oh, sure. Okay. Yep. Yep. Yeah. So basically, the way to explain this is that there are two subscriptions. There's the main subscription from which over which data is flowing, and that subscription is going to be probably not cut up to head, right? Because you're doing some processing on this data, and this processing is expensive, so you don't know what's in the backlog. We have a second subscription that's a metadata-only subscription, where we only care about the event times of the messages themselves. And we use the second subscription to inspect the backlog of the first subscription. We do this by looking at the messages that are newer than the oldest unacked threshold of the original subscription, and we use those messages to establish the watermark by looking at their event times. One thing you'll notice here, I didn't get into this because there's a lot of detail. One thing you'll notice is that this is an overestimate because some messages from the original subscription may have been processed, but they will still delay the watermark. So it's an overly conservative estimate. It's still correct, but it may be more delayed than we could make it with further refinements. Does that? Yep. Mm-hmm. Yes. Oh, I will publish them. Good point. I will publish them, and let's see. I'll find a way to make sure that that's available to the rest of you on some main page. Yeah. Any other questions? Yes.
Do you have any updates on me coming at the top of the project?
That's a good question for Tyler or Ken in the back. Could one of you comment? Ken. Okay. Let's talk after. Okay. Cool. Any other questions? No? Great. Thank you all.
Thank you, Slava.